Hi, nice to meet you. My name is Hagen Wille, and I'm leading the algorithm development team for monitoring solution at MSD Animal Health Technology Lab. In the cube next to me is sitting Dr. Jan Friedman, who's a veterinarian, and together we develop machine learning-based health monitoring solutions for cattle. I will talk about the challenges we have faced during data collection and training our algorithms, and the technical solutions we developed to overcome those. But before going into details, let me give you an overview of our company, who we are, and what we are doing. MSD is a large pharmaceutical company with more than 70,000 employees worldwide. A significant part of MSD's business is the animal health division, which manufactures drugs and vaccines for animals. And it also develops technical solutions for almost any animal that we are interacting with. Every species requires an individual solution. So the technologies that we are working with, they range from computer vision for detecting sea lice infestation in salmon farms based on pictures taken with underwater cameras to genetic phenotyping for tracing back the origin of meat and dairy products. I personally work with signal processing and classical machine learning to develop monitoring solutions for cattle. For whom do we develop such a solution? The life of the farmer has changed a lot in the last decades. He needs to manage more and more cows with less resources and time, so he would like to have some help that allows him to focus on those animals that need most of his attention. Like all of us, the farmer became more tech-affine. Everyone has a smartphone or a tablet, and he's expecting to have access to insights that we are generating with a technical solution from anywhere and anytime. From that, we derived our goal. We want to alert the farmer about sick animals as early as possible, preferably even before he can see it with his eyes. Introducing SenseUp, our monitoring solution for cattle that keeps track of each cow's health 24/7. I will focus in my presentation about the development process for the monitoring tech that you can see here on the left ear of that lovely cow. The task of the tech is to measure the motion of the animal and to infer from that motion the behavior. So both the sensing and the processing of the signal takes place on the device that you see here. The behavior information is then transmitted via Zigbee or LoRa to an antenna in the farm. And from there, it is processed further on a server solution or on cloud-based application. The farmer has access to his insights, like the reports and alerts that we are generating via a web interface. And that's how we solve the problem that he has access to his data anywhere, anytime. As complicated as it is to design such a system, it's even more complicated to train an algorithm for such an application. And this has to do with the environment that we're dealing with. If you have been in the farm, you notice that all those animals, they interact with each other and the environment, so they create large forces. If you want to put some technology on an animal, it needs to be very robust and durable. Also, you have water everywhere and acid coming from the manure, so you want to protect your electronic from that by sealing the device. If you put a sealed device on the animal, it means you have no access to the battery, you cannot replace it or charge it, meaning you have to live with the one battery charge that you initially put there. If I tell you that we expect from our product to live for 5 years, which is roughly the life expectancy of an animal, then you get an idea for how much we pay attention to power consumption. And this is the constraint that limits everything. We have limited CPU power, we have limited communication and limited sensing just because we need to work with one battery charge. Luckily in the company, we have very talented pool of hardware designers, mechanical and electrical engineers that designed the system that you saw, and a lot of software developers that take care of the front end and back end solution so that the farmer has a seamless experience. In that environment, we want to do also data collection. What is the data that I need for developing an algorithm for the solution that I present to you? I'm interested in the behavior of the animal, for example, eating, and I would like to know what does the signal look like when the animal is eating. On top of that, I would like to know if the animal is healthy or sick while it is eating. To gather that data in a large variability and to help me conduct such a trial, I'm consulting my expert friend who is sitting next to me because he knows much more about the animals than I do. So I'm talking to my friend, the vet. Hey, Eran, how do we do a trial? What do we need to pay attention to? And Eran writes a protocol for data collection. He, for example, introduced me to the fact that eating can be different depending on the type of the food that the animal is eating. That chewing hay is different from picking up grass from the field. So also the sensor signal will be different. And if I want to make a good prediction for eating, I need to know about that variability. Of course, the domain expertise of Eran is this health situation of the animals. So he knows all about diseases of the animal and which symptoms they have. And he helped us to develop a scoring system that ranks the diseases according to severity. Other things that I learned from Eran is affecting the way we conduct the experiments. For example, I did not know that cattle are prey and perceive humans as predators. So they change their behavior in the presence of a human observer. Also, the environment has a big impact on the behavior of the animal. Talking about weather and seasonal effects. In the summer in Israel, for example, it's very hot, so animals are resting more and have problems panting, breathing. Whereas in the winter, they are feeling comfortable, they are more agile and active. So you want to cover that seasonal component in your trials. And if you cannot do it by collecting data all over the year, utilize maybe the southern hemisphere for doing data collection. For example, while we are talking, we are having a trial going on in South Africa. In the end, what I get from Iran is a structured data that tells me which animal is healthy or sick when. So I have a labeled time period for every animal that I can use for training. So with the help of Iran, I'm covering the observation part of the data collection. But what about the signal? How do we get the signal from those tags? Initially, we designed the system to also transmit the raw signal out. And this was okay for trials with one or two animals. As soon as we upscaled the process and did trials for an entire farm with up to 1,000 animals, there was too much collision of messages coming, and we realized there's not enough bandwidth for transmitting the signal from all the animals out. Because we want to have lossless communication, we rely on the signal to be complete. It did not work. So we had to change the strategy, and we developed special recording tags where the signal of every animal is written to an SD card that is inside the tag. Having all that in place, we are conducting now trials with an expert field team. Those are usually former farmers. They know exactly how to handle those animals that can be dangerous to a non-expert like me. And yeah, they have fun. They are riding horses. They are with those animals in the field. They are observing them from the distance with either cameras that are mounted or on drones. But most importantly, they keep track of which tag is installed on which animal, when, and where. Initially, we did that also with pen and paper, but with larger data collection trials, we realized we need a more professional solution. And we were looking for something off the shelf, did not find anything that meets our needs. We want to store together with the installation information, also maybe pictures of the animals, little videos that tell us about the condition in the environment that we're doing experiment in. We developed something for ourselves. We call it the research management system. It's a server-based application that we have as a front end for every developer mobile application. So if I do a data collection trial in South Africa, I just register with NFC the tag that I want to install, take a picture of the animal, and it's automatically uploaded into that RMS system. After the trial is over, it's harvesting time. We are taking off the tags from the animals, and now we need to process them. We need to extract the signal from each board to get it to the computers. So here you see how the result of an experiment with more than 600 animals looks like. It's a rack full of tags, and we need to process them one by one. In order to speed that up, we developed dedicated hardware that allows us to parse those tags in parallel. We call that machine the toaster because you close it in order to connect all the pins to the motherboard. And then it's in a matter of seconds to download the SD recording. This is for the signal. The videos we process with an online annotation tool that we also developed ourselves. It allows behavioral specialists to watch the videos from wherever they want when they want to work from home. It's very convenient. But not only is it just a video annotation tool, it's also a tool that allows us to register each tag to the animals that we see in the video. Specifically, we want to register the recording of the animal that we see in the video to the video, so that when we annotate the behavior that we're interested in, like here in that case eating, it's automatic. This annotation can be transferred directly to the signal. Okay, so this is the data collection part, and now it arrives to me on my table. What do I need to do with that when I want to develop the algorithm? Very briefly, my job is to convert the accelerometer signal to behavioral data on a per minute basis. We use an accelerometer because, as I want to remind you, we are living on a single battery charge. And I'm interested in making an inference on the device. So my job is to write a dedicated code that is executed on the device to make a prediction every minute if the cow is now eating or if she's ruminating or just active in general. So here's an example of the data that I'm dealing with. This is a recording of a little bit more than an hour. In the bottom, you see in the signal from the 3 axis of the cow. And it's already married with the behavioral data. Different behaviors on the upper line have different colors. With the handcrafted features, we are teaching a classifier. We're doing supervised machine learning. And the tricky part was to tailor that solution to the specific architecture that we are using and the limited computational time that we want to allow the tech to make an inference. As you can see here, we have a good agreement between our prediction and the observation. And initially, it was good for 80% of the animals. We realized that at some point, we also need some adaptivity that we were able to add to our text. And then since then, we had a very good confusion matrix. But I want to tell you that looking at the confusion matrix alone does not tell the whole story. So how does the whole story look like? Here you see an example of a cow that got our tag at the first day it was born. And we're making inference about the cow's behavior in the first 11 weeks. The data is arranged in a daily routine graph, meaning every row is a day from midnight to midnight, and time progresses from top to bottom. So in the first row, it's born, and in the last row, it's 11 weeks. Pay attention to the light purple that you see in the beginning at 6 o'clock, and that shifts over the time slowly to, let's say, 9 o'clock in the morning. This light purple behavior is suckling. So it's when the animal is drinking from a bottle. And the context information that we get here from looking at the data as a whole is that while it is getting older, it starts to drink the bottle later. As we learned from talking to the farmer, this is actually what they really do in the farm. Like they have the routine of always giving the youngest animal the bottle first. And while the animal is already 6 weeks old, it's not the youngest animal anymore. There were newborns that get the bottle earlier. And this is the reason why our animal is fed at week 6. So the context makes sense. The states that we are predicting really represent what the animal is doing in the farm. Can we use this data for more? And yes, we are interested in the health of the animal. Here you see in this box an anomaly in the animal's behavior. If you noticed, the suckling behavior is not present both in the morning and in the afternoon. So this animal refused the bottle. And this is an anomaly that we can alert the farmer for. So we have an algorithm that signals this as a health event to the farmer. This is how it looks for the farmer. As soon as index is lower than a certain threshold, which you see here as the red line, the animal is alerted, the farmer is notified, he goes and checks on the animal. He realizes in that case the animal had diarrhea, did not feel well. He gives this animal some drugs. The animal recovers, feels better, and we see that in the behavior that we are predicting, that the animal is back to normal, and we remove that animal from the report. Some key findings or key takeaways that I can give you from developing such an application. Even so, you have limited resources like computational power, limited communication, and limited sensing. It is still possible to develop a sophisticated and efficient algorithm for such an environment. It requires some hand tailoring. You cannot take an off-the-shelf solution, but yes, it is possible. Maybe you need to develop or some dedicated tools and machinery if you want to do large-scale data collection. So in our case, we developed the RMS to keep track of all the trials, and we had the toaster for processing the signal as quickly as possible. Something that is really important is that you need to cover data variability. Design the experiments in such a way that you cover most of the natural behavior. I mentioned weather effects, seasonal effects, but also food types. And this will make your product successful not only in 80%, but maybe 99% of the animals that you put it on. Don't rely too much on the confusion matrix. Look at the context that your data provides to avoid overfitting. Like I've showed you the example of the animal with the routine of the suckling. You should give that higher value than the confusion matrix. Because in the end, it's the large-scale statistics that matter, not the tiny accuracy that you measure with confusion matrices. A key success factor is working with domain experts. And this can be difficult. Like in a marriage, you have ups and downs. You need to talk constantly about our problems and attack the problem from different aspects, try to look at it from different point of views. And you will develop over time your special language to do that, to bridge the technology domains. For example, with Iran, when we talked about AI in the beginning, he had something completely different in mind because in veterinary medicine, AI stands for artificial insemination. And that's, of course, not what we are dealing with here. All right. Thank you very much.